Oh, there we go. All right, so our plan for the next few days, today we're just going to look at part of Chapter 11, just the stuff that involves intermolecular forces, based on the fact we just talked about what is polar, nonpolar, things like that. Why do we care? Intermolecular forces. Friday, we're going to do a review for the exam. So officially, it is optional because there is no group quiz. But it's going to be the place where I tell you pretty much everything's going to be on the test and answer all your questions. So
show up.
I would suggest showing up, but it's not required. Yeah.
The next Friday will there be a group quiz?
Nope.
Okay.
Probably not, because we won't have covered very much material to have on a quiz. Yeah, Monday's the exam too. It's going to be Dr. Washington. It's going to be proctoring your exam. She teaches Gen Chem. She'll be more than happy to answer any of your questions if you have them. Wednesday, I'll be out of town. There'll be no class. However, my plan is for right now to pre-record the lecture that I would have given on that day. That way, officially, you don't have to be in here, but you can watch the video, and then we'll talk some more about Chapter 5, which is gas laws. So how many people have done gas laws? PV equals nRT. Okay, we're going to be doing that. So if you haven't done it, no big deal. If you have done it, start that Wednesday pre-recorded lecture will be on my website. You can just catch up on what is a gas, why do we care about gases, fun facts about gases. Gas laws are clearly not my favorite. They're not my least favorite, but they're in the bottom 10. They may even be in the bottom 5. They're real down towards the bottom. That's right. Other stuff is way more interesting, like intermolecular forces. Any questions on what we have coming up for the next little bit? I have all your quiz. I have a bunch of quizzes to give back to you, so do not leave today without getting your quiz so you can study from it. Yes, ma'am.
On the exam, will you give us H and C for the...
Yep. I'll give you the constants that you need. You need to know the equation and how to use them, but I'll give you the constants. So, mostly the reason for that is that the end of the semester test is a standardized cumulative exam where they only give you the constants. And so I'm just trying to get you in the frame set of knowing the equations and being able to use them correctly. So there's no surprise at the end. All right, let's talk about some intermolecular forces then. So let's see here. All right, so we talked about the 4 types, 3. How many did I have the other day? 1, 3. All right, 3 types: dipole, hydrogen bonding, ion dipole forces. We did those real briefly. So intermolecular forces originate from interactions between either complete charges. What kind of a molecule has a complete charge on it? Starts with an I. Yeah, these would be ions. Then we also be concerned with partial charges and temporary charges. So partial charges are the ones we've just finished talking about. These are going to be polar molecules. And then temporary charges is kind of a special case where it's not an ion, it's not a polar molecule. It's most likely nonpolar, but it can have a temporary dipole moment. So we'll look at interactions amongst these 3 different types of molecules. So if we look at, for example, a bond versus an intermolecular force in terms of just thinking about space-wise. So looking at the difference between a OH bond and 2 water molecules. So here is water, here's oxygen, here's the hydrogen, here's the hydrogen, hydrogen, oxygen. Quick question, what Vesper shape does water have? Bent, because it has these 2 lone pairs over here, so it would have 4 electronic groups around it, but 2 of which are lone pairs. Good? All right, so looking at the difference between the distance of a bond and the distance of two molecules. An oxygen to hydrogen, what type of bond is that? This one's a hydrogen bond. An oxygen to hydrogen, is it an ionic bond or a covalent bond? Okay, the oxygen bonded to a hydrogen, this guy right here is a covalent bond. Because they're sharing electrons equally. Bason's covalent, is they a polar or non-polar bond? Polar, it is a polar bond. How would you know it's polar based on your periodic table? Oxygen's way more electronegative than hydrogen. Okay, good. Just pulling some things together. So it happens to be a polar covalent bond. Let's see. Guess I'll write it this way. So a covalent bond is between two atoms that are very closely spaced together. So this bond is 96 picometers, right? Very small distance. The distance between two water molecules is pretty much 3 times as much. It's 300 picometers. So the space between two molecules is much larger, between 2 and 3 times as large, typically. So that tells us that these two water molecules cannot have the same kind of interaction as this oxygen-hydrogen. These two are closely spaced. They're going to share electrons. They made a polar covalent bond. This hydrogen, this oxygen are too far apart to make a covalent bond. But they are close enough that they can at least interact with each other. And so that interaction is called an intermolecular force. So, larger distance, weaker forces. So an intermolecular force is not nearly as strong as a bond. You can think about it this way. If I was going to apply heat to this system, assuming all these waters were in the liquid phase, what temperature does water convert liquid to gas? 100, right? Because I'm going from a liquid to a gas, so I'm boiling, so water boils at 100 degrees Celsius. So at 100 degrees Celsius, I'm going to break up these intermolecular forces for water, break up the intermolecular forces so that they become liquid into gas. I would have to heat water to 1,000 degrees Celsius to break this bond. That kind of gives you an idea of how much stronger a covalent bond is compared to this intermolecular force. I would have to heat water to 1,000 degrees Celsius to break the bond. So the bond's much, much stronger than these intermolecular forces we'll talk through. All right, so there's going to be 3 main types of intermolecular forces we'll look at. Firstly, let's look at dispersion forces. This is an intermolecular force found between all molecules. Sorry, that's kind of fuzzy. There we go. I don't know why there's a double S. Oh, that's why it is. One intermolecular force present in all molecules and atoms is the dispersion force. So a dispersion force is due to the fluctuation of electron distribution around a molecule or an atom. Says, everyone familiar with the word fluctuate? Right. Graphically, it looks like this. It's not really a graph, that's just me moving my hands. That'd be fluctuating, right? So if you imagine a fluctuation of electron distribution, it just means that the electrons are obviously hard to find, right? And sometimes they may all end up on one side. Sometimes they all end up on the other side. Sometimes they're evenly spread out everywhere because we can't know exactly where they are at any given time. So this, in another way of putting it, so at any one time, the electrons may be unevenly distributed, either around a single bond or around the whole atom or around the whole molecule. So if they are unevenly distributed and they all, for some reason, all end up on one side for an instant, what charge would that side have? All the electrons are on one side. It would be negative. So this means sometimes the molecule or atom, I guess we'll, just to be consistent. And what do these little crazy D's mean? Little change, right? So these aren't big deltas, these are little deltas, so little change. They will have a little positive end and a little negative end. Unlike a dipole or a polar molecule, it's not true all the time. It'll just be like for one hot second, positive, minus, and then the electrons redistribute. It'll be evenly again. And we call this a temporary dipole. So those are these non-polar molecules that typically wouldn't look like they have a polar moment. But based on the fact we don't always know where all the electrons are, they can instantaneously be partially positive, partially negative. The magnitude of a dispersion force depends on how easily an atom or molecule can polarize. So, this magnitude of the ability to polarize is called polarizability. That should make sense. The ability to polarize. But polarizability is this. The magnitude of dispersion force. So how easily can you move those electrons around? Polarizability as a trend increases with the number of electrons. So if you think about some of our bigger elements or bigger molecules, there are more electrons, which means the probability of them all ending up on one side is greater than would be if there's just like 3 or 4. Right, 3 or 4 will typically always be evenly spread out, but if you have an element or a molecule that's down here like barium or tectinium that has like 5284 electrons zipping around it, potentially there's a greater chance that a majority will end up on one side and give it a partial positive, partial negative. So, what also increases as we look at our atomic numbers? What also increases with increasing number of electrons? A few things. Take a few answers. I heard a lot of people at once. I'm assuming you said the 2 right things. So, increasing number of protons. And if the number of protons, number of electrons have increased, what else has to have increased, most likely? Neutrons. If the number of neutrons, protons, and electrons have increased, what is the other thing? Oh, I can't write and talk at the same time. That's not spelled right. Neutrons. Atomic weight. So polarizability increases the number of electrons, which also directly relates to increasing mass. So a heavier molecule, or atom, has a greater polarizability, which is what I'm showing here in my nifty little chart. So, mass of CH4 is 12 and 4, so 16. About 16 grams per mole AMU. If I have CI4, let's see, iodine, it's 126. That'll take a little bit of work, hold on. 4, 5, 2, 4, 504 plus 12. Really, I did not do this ahead of time. 516-ish. So CH4 is much lighter, which means it is the least likely to polarize. It is the least likely to polarize. It is definitely nonpolar, and if it's nonpolar, it has a lower melting point. Can you follow that little flowchart logic? Maybe. So CH4 is the least mass, which means it has almost zero ability to polarize, which means it is always nonpolar. Nonpolar things only have dispersion forces, which are very weak. And if they have weak dispersion forces, it means it's very easy to get them to melt. Does that flowchart make sense? So then if I have CI4 and it's very heavy, what does that tell me about its polarizability? High or low? High polarizability. What does that tell me about dispersion forces? A lot or very little? A lot of dispersion forces. A lot of dispersion forces means it requires a lot of energy to break up those dispersion forces, to push it into the next phase. Good, that flowchart makes sense? Okay. In that case, let's look at the next force. Dipoles and dipoles. So, a dipole-dipole force is an interaction between two polar molecules, which should make sense based on its name. So, polar molecules have permanent dipoles, which we've looked at some of these before. We looked at, what did we look at? CH3Cl was one of our examples. Oh, we just had water. These are both polar molecules. So they have permanent temporary positive and temporary negative. I have this on the next sheet. All right, so based on what we just said about polarizability, that the greater the polarizability, the higher, the stronger the forces, so the higher energy required to melt. Polar molecules have higher melting and boiling points. Than nonpolar molecules. So what is it about the polar molecule that causes them to have stronger attractions to each other than two nonpolars? You can answer it to yourself. So let's take a look at two molecules and see what might be going on between them. Let's look at this guy and this guy. Okay. First thing I want to do is draw the Lewis dot structure of this one. So what atom goes in the center of this CH2O? Carbon. So if that's in the center, my hydrogens are happy. Is my carbon super stoked quite yet? No, what does it need? It needs another bond. And then give some lone pairs off that guy. Okay? That seems reasonable. This one, we haven't done very many like this, but the structure looks like that. Is everybody happy in that version of the Lewis dot structure? Carbon's happy, hydrogen's happy. My mouse is in kind of a weird spot. There we go. All right, my next question is, are they polar or nonpolar? So, looking at this top one, are there polar bonds? Yes. How many polar bonds are there? Two types. I'd say two types of polar bonds. Okay, looking at my carbon to hydrogen, which way are the electrons flowing? To the hydrogen or to the carbon? To the carbon. All right, looking at the difference between carbon and oxygen, are the electrons flowing to the oxygen or back into the carbon? Bless you, bless you. So, does this molecule have an overall dipole moment? Yes, it does. It is a polar molecule. All right, this bottom one. Does this bottom one have any yes or no polar bonds? Has a few. Okay, is this one in the center a polar bond? Why do I know it's not polar? It's the same atom on both sides, right? Okay, good. Okay, so then looking at this, it's going to be one of these, one of these, one of those, one of these, some of that, some of this. Is my bottom molecule polar or nonpolar? It is nonpolar. All right, next question. What is the molar mass of this guy up here? Let's see, that's 12, that's 16, 12 and 16, 28, 30? How about 30? All right, what about this one? What's its molar mass? 30 also. So besides the polar and nonpolar, the exact same mass, right? So if there's any difference in force between the two of them, it's going to be based on the fact that one's polar, one's nonpolar. So if I imagine what's going on if I had a mixture of two of these guys, right, we said all the electrons are kind of flowing up this way, so this end's going to be the partial negative. And this end over here, partial positive. If I put another molecule like this in the same vicinity, how will they line up? You can imagine that's going to look like this. Right? You got your positives and negatives all lining up. When they line up like that, that is a pretty firm structure. Right? That's going to be a little bit harder to break apart than you would expect. All right, let's do the same thing for down here. Let's say I have two of these guys. So I have one. I'm going to put another one in its vicinity. Is there any particular orientation going to be forced upon the second one? No, right? Because it's nonpolar overall. So it could be, because they're all just H's. It probably won't do this, but it could. It could slide in like that. Or it could slide in a different way. Maybe it lays on top, or maybe it comes in on this side. Right? There's no definite orientation if there's two nonpolar molecules. So, based on that, which one of these should have the higher boiling point? Which one will require more energy to break up the intermolecular force? The polar or the nonpolar? The polar. That is correct. Which, did I say that on the other side? I did. True. Good. We proved what I said earlier. Excellent. And if you're fascinated, it turns out the boiling point of this guy equals negative 19.5 degrees Celsius. What does that tell you about what state of matter are they in typically at room temperature? If they boil at less than 0. They should definitely be gases. Yeah. We're working our way up to gas laws. See, gases. Yeah, if they're boiling at below 0, it really means they're going to be a gas all the time. Good. Any questions on our dipole-dipole forces so far? Okay. Polarity is also an important feature to determine miscibility. Does anyone know the term miscibility? What that means? It means ability to mix without separating. So polarity is a key feature in determining how well two types of molecules will mix evenly within each other. So like we looked at before, we have water, which is polar. We had that molecule that we had just 2 seconds ago. If I put even equal amounts of both of these into a beaker, they will not mix. They'll separate. And the polar molecules only associate with other polars. And the same thing can be said for the nonpolars. The nonpolars only associate with other nonpolars. This is so true that even has its own nifty phrase. Yeah, like dissolves like. Isn't that a fun phrase? It doesn't really tell you much of anything, but that'll be the phrase they use when they talk about this. That if I put in a third compound, let's say I put in, it's a good third we'll do this one. That one's easy. I have methane. If I add methane to the mix, who will it choose to associate? Water or the other compound? We haven't learned how to name the other compound yet. The other compound. It's going to choose to hang out with the other nonpolar compound. So that's all that means. Polarity determines how well two things are able to mix. All right, then let's take a look at our third force, which is hydrogen bonding. Hydrogen bonding is a special force, but technically a subcategory of dipole-dipole interactions. One molecule must be a hydrogen. And that hydrogen has to either be stuck to a nitrogen, an oxygen, or a fluorine. And then the other molecule must contain an oxygen, a nitrogen, or fluorine. So in terms of cute cartoons, it's going to look something like this, where I have to have, we'll do this one. All right, there's the rest of the molecule hanging off this side. Doesn't really matter what the rest of the molecule is. On the end of it is an N bonded to an H. Over here, we'll do water. The hydrogen bond is going to form here between the hydrogen attached to a nitrogen and the oxygen. And again, this comes from electronegativity. So if I look at the NH portion of this molecule, will the H have a partial positive or partial negative, typically? Almost always partial positive. I know everyone was screaming in their head. They just didn't want to be the person who said it out loud. I appreciate that. So we have that partial positive being associated with a partial negative here in this hydrogen bond. So hydrogen bonds form because of the large difference in electronegativity between hydrogen and the oxygen, nitrogen, fluorine. Where hydrogen is always going to be our partial positive, and these guys are always going to be our partial negatives. So this is a critical feature, especially when we talk about water, because water can hydrogen bond to itself, right? Because it can have it happens to have the ability to hydrogen bond to another molecule just like itself. If it's able to do that, would you expect a higher boiling point than expected or a lower boiling point than expected? Should be higher than expected, which is what we see on our little trend of boiling points. So here we have, I'm looking at period 2, 3, 4, 5. So if I look at this bottom line, I got period 2 is along here, so I have CH4, then I go down one, SiH4, then I go down one, germanium. All right, so I'm looking at this column, carbon, silicon, germanium, tin. And the boiling points increase with increasing mass, which is what we saw earlier. And then we have our crazy guys over here, which mess up our whole nice trend line. NH3, which is this guy, HF, which is over here, and then water. Blows everybody else out of the water. I practice my jokes upstairs in my office just to make sure that they sound funny. They do. They do sound funny. I don't want to have a joke that falls flat, so, because it's being recorded forever, or as long as YouTube exists, or I delete the video. All right, so here we have water, which has a way higher melting point, boiling point than expected, because it's able to hydrogen bond to itself very strongly. All right, last one. This is the last thing out of chapter 11. Ion dipole forces. As the name implies, it involves an ion and a polar molecule. So all the naming in this chapter should be very straightforward. It's either two dipoles, two non-dipoles, an ion dipole, or something with hydrogen. So this occurs when you have an ionic compound mixed with a polar compound. In reality, this is most often going to be a salt dissolved in water. So, if it's a salt dissolved in water, which one of those two items is the polar compound? Good. Just checking. Everyone's been paying attention for the past, I don't know, 3 weeks. Water is like my go-to polar compound because it's easy to draw. All right, so then that leaves salt as my ionic compound. So, what's my favorite salt? We'll do sodium chloride. I'm sure that's everyone's favorite salts, the edible one. Like you can do potassium chloride if you want to be a salt-free diet, which don't get me started on that's ridiculousness because it is salt. Next time you go to your supermarket, go over to the salt section and look for the no salt salt. It's because it's potassium iodide instead of sodium chloride, or potassium chloride instead of sodium chloride. It's still salt, is a salt, it's just low sodium, meaning no sodium, because it's potassium. Hopefully by the end of chemistry, you'll be, if nothing else, a wise food shopper and not get suckered in to the, chemical-free cleansers. I don't even know what that means. Because everything's a chemical. Water's a chemical. So if you're using water to clean your table, you have then used a chemical cleanser.
Did you see them from false advertising?
Probably. Yeah, because at least misleading. So that's why you gotta be careful, especially when you watch your infomercials. Who doesn't love infomercials? You gotta be careful because they're probably not telling you their science is shady at best. Mislabeled. Like when it says 0 trans fat, it just means they didn't mess around with the fats in the first place. All fats are not trans. If it is trans, it's because a human messed around with the fat. And trans fats aren't bad. They're just not cis fats. And cis fats doesn't sound very sexy to talk about. Right? You can't say 0 cis fat because that just doesn't roll off the tongue the way that 0 trans fat sounds. So, anyway, that's a whole other lecture. That's actually why I lectured today in biochem about fat and fat-soluble vitamins and how you can overdose. Turns out you can overdose on vitamin A. If you eat too many sweet potatoes, carrots, whatnot, your skin will turn orange. That has happened to several people. And it's because it's a fat-soluble vitamin that gets stored in your skin. And so you will turn slightly orange. But your skin will be super, super healthy. Because vitamin A's job is to rejuvenate your skin cells. So which is why if you take a retinol A for those Oilable Lay anti-aging commercials, it's just vitamin A that you're smearing on your face. You can do the same thing if you just eat a healthy diet of your orange vegetables and leafy greens. So I saved you like $30. So there you go. Back to what I was actually talking about like 10 minutes ago. All right, I got my sodium chloride hanging out in some water. Oh gosh, I love food chemistry. I love food in general. The chemistry of food.
Do you bring food to class sometimes?
I should probably to help because it is lunchtime. I'll think about it. I was telling my biochem class this morning my favorite food is anything that's on a stick, which is mostly food at the fair. I do love fair food. My favorite thing because I want to be able to eat it while holding it and walk around. And so, because someone asked me if I eat healthy, and the answer is definitely not. Definitely not. Corn dogs. It doesn't love a corn dog. So, or cheesecake on a stick that's been fried. You take the cheesecake bite.
That's so good.
It is so good, right? Or the other one I like, which you can't find here, it's because I was in Minnesota before I got this job, was hot dish on a stick, which is a meatball, 2 tater tots, battered, fried, and is served with a side of gravy. It's like a whole meal, all on a stick. It's pretty amazing. Pretty amazing. So I would recommend if anybody, is thinking about opening up a food truck. There you go, hot dish on a stick. If you're listening, internet. Yeah, hot dish on a stick. Delicious. Oh, so anyway, here I am. I'm doing this, right? And I got that. I got my sodium and my chlorides hanging out. Now my water, I'm going to have this guy associated this way. And I got associated that way. And then I got the opposite over here. So I got my polar water associating with my ions. where the oxygen and sodium tend to line up, and then the chloride and hydrogen tend to line up. That's why salts dissolve so well in polar compounds, because the polar compound has enough permanent dipoles to dissolve the salts evenly. All right, so the last thing I'm going to do today is, because we are reviewing on Friday, I'm going to give everybody a small sheet of paper. Think of at least one question. I don't want your name on it. I just want to know at least one or two things that you are confused about coming up on the test. That way I can specifically address them on Friday. So either it could be a topic, it could be a specific problem you didn't get, or anything, whatever you have. And while you work on these, I'll have just this left of it. Just in terms of water over this, probably ought to be here. All right, so any question you can think of, that anything that's up to the exam.